Tesla's full self-driving does so well under so many circumstances that it seems very odd to many people that it does so poorly doing things like creeping and accelerating into intersections when it needs to. But there's actually a reason, and it's buried deep down in the way that neural networks work, and it actually is a bigger problem than many people think, and I don't know exactly how Tesla's going to solve it. Let's take a look. Hey y'all, it's Dr. Know-It-All. So I'm going to get a little bit into the way neural networks work today because I want to talk about this in some detail and explain the reason why many people, including me, feel like the car does a bad job of creeping, which means kind of easing forward to look around and decide whether it's going to do something. And then especially as the vehicle starts to accelerate into an intersection or across a dangerous type of situation, why it often seems very, very slow. So as most of you know at this point, Tesla uses a ton of neural networks to be able to do their full self-driving. The vision system is based on that. A lot of the intermediate products as it's figuring out the world are based on that. And then even policy decisions like what it's going to do and when it's going to do that are starting to be based on neural networks. Although I still think a lot of that actually has some C code and some C++ code. But as Andrej Karpathy said a couple of years ago, Tesla is depending more and more on software 2.0, which is the idea of neural network architectures instead of traditional hard coding. And if you haven't caught my episode about that, you should definitely check that out if you're interested. So what this means is neural networks and the way neural networks work has become very important to the way that Tesla's full self-driving operates. The advantage of it is that it makes a much more human type of situation, a much more human type of driving available to us, which means that it's able to deal with fuzzy, uncertain sorts of situations very, very well. But what it doesn't do is it doesn't do relatively extreme actions extremely well. And some of those relatively extreme actions are things like creeping slowly when it needs to do that to look around and figure out what's going on and decide when to move, and then to move rapidly when it decides to move. And this episode, actually, I'd been thinking about it for a while, but the inspiration to actually go ahead and do it was from yesterday's video, which is linked right up here, which is all about my left-hand turn. So I was doing a left-hand turn that's somewhat similar to Chuck Cook's left-hand turn, and the times that the vehicle failed, the FSD 10.69.3.1 failed, was in situations where it needed to behave with more certainty. What it was doing instead was kind of trying to find that middle ground and not be assertive. So I'm sure a lot of you know, relatives or acquaintances or coworkers or something who have that sort of character flaw where they're unable to make decisions. Somebody once told me a long, long time ago that the wrong decision is far better than no decision, and I've really taken that to heart over years. I found that that is very, very true. Oftentimes, even if you make a poor decision, you can go back and fix that later, but at least you've made a decision and things can move forward. If you don't make any decision at all, then you're just stuck in this wishy-washy land where nothing actually happens. So, I guess you get life advice out of this episode as well. But the problem that happens for neural networks is that neural networks, the way they're designed, remember that they're just a whole bunch of little knobs. They're a whole bunch of little weights that you take your input, in this case, some video images or a sequence of still images that are on 8 cameras. You feed that into these neural networks. I'm going to abstract this a great deal, but you feed them in, a whole bunch of little multiplication and additions are done, and then out pops a decision. It's like go this fast, turn this much, brake, accelerate, do things like that. So it pops out some information to the policy network. In other words, the thing that actually goes ahead and does the driving, that makes the decision about what to do. But the way that it does this is very different than the way you might think about it. So if you're familiar at all with hard coding, with traditional software 1.0 type of coding, you can get a thing like, if X is greater than 0.5, then do this. That's very, very certain. And if you get something that ends up giving you an answer of 0.63 or something, then you know that you make the decision that is the secondary decision, right? It's like, if this is greater than this, then do this. So you can make the decision and you can do it with a great deal of certainty. The way that neural networks work is probabilities. Everything is a probability. So what it says is when it sees a group of pixels that look kind of a bluish color and look like they could be a car, what you're getting is in that portion of the image, you're getting a probability that that's a car. So it's saying, the probability that this is a car is like 84% or something, right? 0.84. So that's kind of what pops out of the neural networks. Even more importantly, internal to the neural networks as they're being trained, remember, all of these things are just little weights. They're little knobs that the input image and the input information is being multiplied by to create this probability. And the way that neural network training traditionally works is it punishes outliers. So what that means is you want something that represents the most overall of the input data. So as you're inputting images, again, I'll use the cat and dog thing because why not? Everybody likes cats and dogs. So as you're inputting cats and dogs, you have 500 pictures of cats, 500 pictures of dogs. And within that group, maybe you have 50 pictures of cats that look an awful lot like dogs and 50 pictures of dogs that look an awful lot like cats. Well, part of the training of the neural network here is to make a decision about those cats and dogs. So what it's doing is eventually at the end of this, right, you give it a new image it's never seen, and it outputs a probability between 0 and 1 that it's a cat, and then the opposite of that. So if it's 70% it's a dog, then it's 0.7 that it's a dog and 0.3 that it's a cat in this very, very simple two-category situation. But when you have a situation where a cat looks an awful lot like a dog in the image, then what should happen is the probability should balance and you should get something very, very close to 50%. Now, what you're going to get is an answer that says cat or dog, but it might be, 0.51 cat and 0.49 dog. And that's okay. What you're trying to get rid of, you're trying to smooth out any, weights or things like that that are very, very extreme. And that's actually okay. What you don't want to have is very, very high probabilities when it doesn't have the certainty that it has that, right? So if it sees something, it shouldn't be giving you like 95% certainty when the two of them look an awful lot the same and a human being might have to think about it for a while. Where that comes from is that you could have weights, right? So again, you take your input image, the pixels from that image, and it's multiplied by all of these things and they're all added up, right? Again, just hand wavy, but that's kind of in general what happens. But if you have one particular weight that's really big, so let's say all the other weights are less than 1, so they're very, very small negative and positive weights, but you have one weight that's like 10 and it's a relatively simple neural network, that weight will outweigh everything else, which means that it might be like the dog thing, right? So it's like this one neuron that's always going dog, 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 dog. And that's going to be right 50% of the time with your training set, but it's not going to be right the other 50% of the time. And what's going to happen is the loss function that you design that tells it like it's doing a bad job is designed to crush that and make that 10 value get lower and lower and lower to bring it in balance with everything else. So eventually what happens is this regression to the mean. In other words, it kind of crushes everything. It takes those outlying values that are in the neural network and it smushes them down so that they are more or less the same as everybody else. And so everything is just little wiggles, that are going on in these numbers. And you're getting, even if it's a really definite dog, it might still only be like 75% certain that that's a dog and 25% certain that's a cat. And in this situation, that's actually a good thing. You don't want it to be 100%. You don't need it to be 100%. You just need it to be above 50% when it's actually a dog. And so it's doing a good job. What you don't want it doing is confidently predicting that it's a cat when it's a dog or vice versa. And that can often happen when you have some of the weights are just too big. They're too outlying. So what it does is it regresses those things down. It squishes them down to the mean. And that produces things that in the end, when you look at something like a DALL-E 2 image or a Stable Diffusion image, I don't know if you all have noticed, but the images have a softness that real photography doesn't have. So if you're looking at the video of me, and I really don't want to look at me too closely, too old and wrinkly, but anyway, there's a lot of detail in the images that you're seeing of me. Whereas if you had something like Stable Diffusion do, Dr. Know-It-All in Stable Diffusion, that would be a smoother thing. It would look more painterly. And the painterly aspect comes around the fact that you don't have those hard details because those hard details are kind of outlier values and they're generated in a neural network by intermediate weights inside the hidden layer somewhere that are pretty big relative to the other ones. And those can produce those fine details, but they come at the cost of also producing really, really ugly results that you don't like. And so what happens is over the period of training, it squishes those things down and you sacrifice those fine details for the relatively smooth, relatively good overall look. So what does all this have to do with these outlying sort of conditions when you're driving? What does it have to do with creeping and then accelerating rapidly through intersections? Well, think about it. One of the loss functions is what's called jerk. Again, it's that kind of jerking motion that you feel. The FSD team has designed it so that you don't want too much of that. You don't want the passengers in the car to be like, oh my gosh, the thing's jerking around and behaving like, very erratically, things like that. So that's part of the loss function. And so it's crushing that behavior. And what that does is that means as the car's driving down the road in a straight line on the highway, on city streets, etc., it's doing a good job because it's just kind of in the middle. That's the average values. That's the things it's supposed to be doing. But as it's creeping forward, it may not be creeping slow enough. It may be creeping too rapidly because the really, really slow creeping is an outlying value. And that's something that requires weights that are different from the average values. And then especially the situation that I really, really hate is when it accelerates very, very leisurely into an intersection and you see cars coming and you're like, oh my gosh, please go faster. And that is also, in my opinion, again, I don't have inside information, but it certainly seems to me that that is coming from the crushing of these outlying values that tell it it's okay to go fast here. So what it's doing is it's squeezing all of these values. So if you're just driving along in a straight line and following cars and doing this stuff, it behaves very, very well. And almost never do I feel like I need to take over under those circumstances. But as it does something like make a left turn and it has to creep out to see things and it does it too violently and it's kind of jerking like that and you're like, oh gosh, I please do it a little more slowly and gently. That would be nice. But then especially once it commits to the move and it just kind of accelerates slowly into the turn and you're like, please go faster. That is coming about, I believe, because the neural networks are trained, and the way that neural networks train is to get rid of these outlying values. It's like, don't ever accelerate or brake really rapidly. That's a loss. That's a bad thing in the vehicle. And the problem is that under certain circumstances, accelerating or braking rapidly is a really good thing. It's like the wrinkles in my face in, this video image, as opposed to something that Stable Diffusion or DALL-E 2 is doing and not producing those fine details. You actually, under certain circumstances, want those details, those outlying values, but it's really difficult to train a neural network to do that without also destroying its generic or general or average behavior. And that is the issue. And that's the problem that I see for Tesla's AI team. I'm like, that's a really, really difficult thing to solve. Now, as I mentioned in yesterday's video, and I'm going to reiterate here, I have an idea. This is just in my humble opinion. I do not take any, this is just what comes to me as a relatively naive outsider, is that what they could do is they could look at creating a situation where part of the loss function might be how much time you spend in the intersection. This isn't going to really help the creeping behavior that much, but once it commits to the move, if it starts a little stopwatch, right? So if it's like, as soon as it's like, I'm going, click, and it's like 1,000, 2, 1,000, 3, 1,000, and then it's into the lane and it's actually driving forward. If it could start a stopwatch, and then what you do is you punish it, you give it a loss for too much time. So you could look at human drivers as a metric and say, like, when people are in this same situation, it takes them this long. Or you could just literally go like, the longer it takes, the worse it is over a certain amount of time, right? If it takes longer than 1.5 seconds, you start to punish it more and more. But basically, by building that into the loss function, by saying, if you do this, you're going to lose points, essentially, right? So again, remember that the neural network more or less is like a student at school, and the training information, the training data, the training regimen is the teacher telling it whether it's doing a good job or a bad job. So what you're doing is you're having the teacher grade them on a different metric than the person was before. So that's what you're doing. You're adding this in. You're saying it needs to be safe. It needs to make sure cars aren't coming. It needs to do this kind of stuff. But if you start a timer and it takes 3 seconds and it was supposed to take 2 according to the training data, then that's actually given a lower score. That's given a loss, and that's fed back through the network. So that's something that it has to take account of as it's actually training to do the full self-driving. And my thought is that that at least will somewhat compensate for the fact that what it's trying to do is squish these outliers in generic and general driving circumstances, and instead allow it in those circumstances where it's not going in a straight line, where it's crossing some sort of intersection, where it's in a situation where it urgently needs to finish this maneuver. It'll give it that urgency. It would allow the neural network networks to train in a way that would compensate for the fact that under generic circumstances, under general average circumstances, you don't want high rates of jerk. You don't want rapid acceleration. Under certain circumstances, you most definitely do. And when you have a driver that doesn't do that, or an FSD that doesn't do that, it's not only discomforting, it's actually downright dangerous because, of course, people could hit you. And finally, the other piece of this puzzle that's also important that I haven't really mentioned so far, but a lot of people, including me, don't like, is that the car doesn't tend to telegraph its intentions to vulnerable road users. So I drive around my neighborhood, there's kids on bicycles, there's people out walking their dogs, there's people standing next to cars, things like that. The car always goes around them and you can see the little noodle, deciding that it's going to go around, but it does it really, really subtly. Again, it's trying to be very average. It's trying not to go out of its way. It's trying to do everything exceptionally smoothly, which is, fine when you're generating images, but not fine when you're coming up on a person who's staring at you and going like, are you going to get out of the way, or again, you going to hit me? And as a person, right, I'm assuming most of you probably do this too, you tend to move over early and you move over very, very distinctly so that person coming towards you or the cyclist that you're overtaking, those people know your intentions. They're like, okay, this person spotted me, they're going to get out of the way. So again, I believe in this circumstance that somehow creating a loss function where you take account of the fact that you're not alerting the VRU early enough to your intentions also counts as a loss. So this all comes down to compensating for the fact that neural network architectures and neural network training is designed to average. It's designed to squish outlying weights and outlying values to create very, very average and, solidly good output, but it's not always good. Under certain circumstances, you need more radical output. And in order for that to work, the only way that I really know how to do that is to redefine the loss function, to create a loss function that really takes account of that and actually punishes the neural network for not, under certain circumstances, doing more outlying values. So again, I want to be clear, this is from the outside. I don't have any inside information from people at Tesla. This is just my observation, and my observation from training neural networks is that's what it does. And I think that that's the problem that they're having right now, is that it's really, really good for average circumstances. It's not very good for those outlying circumstances. And the only way that I know of to solve that problem is to change the loss function so that it can train on those more outlying circumstances better. Now, maybe the people at Tesla have way, way cooler ways of doing this than I know about, and I wouldn't be surprised at that at all because I can't keep up with all the research. I try, but I can't read all the papers. But there may be some papers out there that do things about, like hard-edged training so that it can do things where there's more distinct differences. I think one of those circumstances, honestly, is what John Emmons talked about at AI Day #2, and I'll put a link to that up here if you're interested, but about the lane creating intersections as more of a language model. And language models have a grammar, but they also have distinct outputs, right? So rather than average things and kind of going like, this is 50% a lane and 50% not, it needs to actually, say this is a word and this is another word and this is another word, and these things follow each other and they make grammatical sense. So that makes really good sense in a linguistic model, and they're transferring that into the lane geometry model. So my hope would be that they can transfer that type of architecture, and again, using a loss function where it's actually taking account of how long it takes you to get through the intersection, that they can use that type of architecture to kind of recreate the way that the car drives. And in those circumstances, it becomes less about, oh, I'm kind of accelerating and I'm moving into this, and more like it's like I'm stopped or I'm going. And that's what's happening, right? This is what a human being does. A human being goes like, I'm stopped, I'm waiting for traffic, and now I'm going. And when I'm going fast. I'm getting out through the intersection and I'm getting into the lane, and I'm going to do what I'm going to do. So the car is better about stopping than it used to be. Certainly it stops and it waits for a while, and it doesn't do that little thing where it's like jerking like it's supposed to go forward. But what it's not doing right now is that like I'm going thing. It's like, maybe I'm going, yeah, maybe I'm going, okay, I'm thinking about it, and then it eventually gets up to speed. So my hope would be that Tesla can either use the loss function, or they can do something more like these language models, or some combination of both, to be able to help the vehicle drive under these more edge case scenarios in a much more assertive and aggressive manner, because it's much less dangerous if it does things, if it telegraphs its intentions, and if it does things with, assertiveness and authority rather than that sort of wishy-washy thing. And again, I believe that that comes down to neural network architecture and neural network training, that wishy-washy behavior is exactly what you're looking for most of the time, but it's not so great when you're driving a car under certain circumstances. So anyway, that's what I think is the problem, and that's what I think might be the solution. Although again, I think that this solution is pretty challenging. So hopefully Tesla's got some ideas and they're working on this kind of thing. I would love to know what you all think about this, especially if you've done some neural network training yourself and have some insight into that. I would love to know if you have alternative methods aside from changing the loss function around as to how to allow neural networks to do things that are not always regressing to the mean. Of course, if you enjoyed this rather geeky video, please do like it so other people can find it, and of course consider subscribing for more of this kind of content. As always, a huge shout out to my patrons on Patreon. Thank you all so much for your support. I really do appreciate it. It helps a ton. And of course, if you want to join the team, just check out the link in the description. And if you're interested in a whole bunch of really cool merch, check out our merch store. Link is in the description. We have TeslaBot t-shirts, the Tesla meme t-shirt, success is a possible outcome, 4680 battery cells. All of that stuff is on t-shirts, mugs, tumblers, and on. So check it out. And for those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Thank you. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a solar roof, a power wall, or anything on Amazon helps out the channel. In the meantime, I'll see you in the next one. Bye-bye.